Welcome back. We've just finished the ALU card in the previous episode. In this episode, we are going to look at the register file card. We will start our journey around the register file card, but I am beginning with the high-level diagram of the ALU because I want to highlight one thing. Notice that when I showed you this, I showed the 4 general-purpose registers of Talos, A high, B high, A low, and B low, which can be used as 4 8 or 2 16-bit registers. But in the ALU card itself, these registers are not there. Their contents go through the backplane connector for all 4 of them, and then there is a buffer, a 74245, and then the ALU gets the individual bits of each of the 4 registers. But the registers themselves were not in the ALU card. Their output was through the backplane connector, but not the registers themselves. So today we are going to look at the structure of the registers themselves in the register file card. And I will do first a high-level diagram to impress on you how simple the whole thing is, even though when we put all the chips together it will look complicated, lots of chips, but the essence, the functionality is very simple. We are going to use an internal bus in Talos, a 16-bit internal bus, divided in 2 bytes, the high byte, or the internal bus high, and the low byte, or the internal bus low. Each one of them is 8 bits, so across the 2 of them we have a 16-bit internal bus. And now we use this convention, IBH and IBL, internal bus high, internal bus low. Now, we need, of course, for the register file card, we need the registers themselves, which are shown here, and they are connected to the internal bus for input. In other words, I can load into a high a value in the internal bus high. I can take the value in the internal bus high and load it into register A high. I can load that same value in B high. And the same thing on the other side for the low byte. I can take the contents of the internal bus low and load them into A low or load them into B low. There is no communication across the 2 bytes of the bus. There is no communication in the register file card. I'll come back to that at a certain point in the future. Now, as we've seen in the previous episodes, the outputs of these registers go straight to the ALU. They bypass the internal bus. They feed straight into the ALU card, all 32 bits, 4 registers of 8 bits. But of course, we also want to put the outputs or the values in these registers. We want to be able to put them back into the internal buses via, via some tri-state buffers. So we can take the contents of A high, for instance, and then control this tri-state bus so as to drive that content of A high into the internal bus high. And the same thing for B high, A low, and B low. So we can control 4 tri-state buffers to put the contents of each of the registers into the respective half of the internal bus. We also want to be able to take a byte either from the internal bus high or the internal bus low and put that byte on the external data bus. So the internal bus is visible only to the CPU, and the external data bus, which is 8 bits, will be visible to other system components, like it will be the bus connected to the output of the system memory, for instance. Also a bus that probably will be used for I/O, input-output. And then we need 2 tri-state buffers, one connected to the low byte and the other one connected to the high byte, so we can select whether it's the contents of the high byte or the low byte that go to the external data bus, which is only 8 bits. And then, of course, finally, to coordinate this whole thing, we need some control logic. This logic will produce the load enable signals for the registers. When load enable is active, and it's active low, then in the next rising edge of the clock, A high will capture the contents of the internal bus high. The same same thing applies for B high if its input enable is active. And of course, the same thing applies to the low bytes as well. And in addition, this control logic has to produce the output enables for these tri-state buffers. And it has to make sure that it doesn't enable two buffers at the same time that will conflict with one another. So there has to be some logic in here to make sure that we don't have bus conflicts, that whoever is enabled is the only driver of the respective half of the bus, or the only driver of the external data bus. So we don't want, for instance, to enable this tri-state buffer here at the same time that we enable this one here, because they will conflict. Both will try to write at the same time into the external data bus. So we need some control logic to make sure that everything is orchestrated. And that's it. That's it. There is nothing more functionality-wise, logically-wise, there is nothing more to the register file card, even though it will look complex by the time I show you the final schematics, because there will be a lot more chips, you have all kinds of details that come up later. But don't lose sight from the fact that essentially this is it. It's as simple as this. Everything else is ancillary, it's details, it's important in the sense that it wouldn't work without you taking care of the details, but it's not really engineering. It's not high-level engineering anymore. It's just that, little details, little housekeeping that we have to make sure is there, but is not a significant part of the design, let's put it that way. The design itself is just this simple: a 16-bit internal bus, an 8-bit external bus, 4 registers, the respective tri-state buffers to deal with bus contention, and a little control logic to make sure that the load enables and output enables are turned on and off correctly. That's it. Let's move now to the first bare bones model in Logisim, the simulator, where we basically transfer this into the actual components in the simulator. So here it is. This is a bare bones but complete model in Logisim Evolution, the simulator I've been recommending throughout this series. Again, links in the description. It's a free open source simulator. You can just download for free and use it. I will be using 7433 register chips. These basically have 8 flip-flops, and it has a load enable, which is this line here. It's quite useful. Let me just move myself around so I don't hide this. This is a load enable input. It's quite useful because only if this load enable is active, and it's active low, does the register acquire the contents of the internal bus high, in this case, on the next rising edge of the clock. Now notice that I am using a naming convention here: internal bus high input and internal bus low input, as opposed to internal bus low output and internal bus high output. Well, what's the difference between the output here and the input here? Well, none. It's the same thing. I'm separating them just because Logisim needs you to separate inputs from outputs. At least in its current version, it doesn't know how to deal with ports that can be both inputs and outputs, that can either drive or receive a signal from elsewhere. So to make a model of this that you can use as a sort of a component in a higher level simulation in Logisim, we have to separate output from input. But you can imagine that this point here is simply connected with this point there physically. The same thing for this point here, the low input physically connected to this point here, which is the low output. They are the same thing. The outputs here just go back here, the output here and here. They just go back to the buses in the center, which is the internal bus. That's all there is to it. I mentioned something now that I forgot to mention when I was showing the same kind of diagram for the ALU card. Everything that I'm showing you here, you can import into another Logisim simulation as a component. So the whole thing that you see here will be hidden behind a little box like the 74245 here, this little box with inputs and outputs. This whole thing here, the entire register file card, can become a little box like this on a higher level simulation, in which I could simulate the entirety of Talos by bringing together a little box for the register file card, another little box for the ALU card, another little box for the address logic card, for the control card, and so on and so forth. So this is why I'm separating the outputs and the inputs, because I want to use this whole thing here later, or I want to enable you to use this whole thing here later as if it were a chip, as if it were a single component hidden behind a little box that you can use in higher level Logisim simulations again. And these just specify what the inputs and the outputs of this block at a higher level simulation will be. Now, so these are the connections of the inputs of the registers, the 377s, to the internal buses. On the other side, we have the buffers that drive the outputs. So say if this buffer here is output enabled, then the contents of register A high will be driven into the internal bus high. Same thing for this. If the output enable of this buffer here is active, it is enabled, then the contents of B high will be driven into the internal bus high, which is this line here. And the same thing applies to the other side, just for the low bytes. These are the two buffers that drive the outputs of the respective registers back into the low part of the internal bus. Here, it's what drives the external data bus. And again, I'm saying external data bus output, because Logisim requires you to separate everything into outputs and inputs, never an I/O. So these buffers here will take either the contents of the high byte of the internal bus or the contents of the low byte of the internal bus and drive it to the external data bus, just like we saw in the previous diagram. And this buffer here and this buffer there basically do the opposite. They take the contents of the external data bus, which I'm marking as external data bus input. It's essentially the same as this, but I have to split inputs from outputs, so this works in Logisim. Takes the contents of the external data bus and drives them into the high byte of the internal bus or into the low byte of the internal bus. So this buffer here takes the content of the external data bus and drives it into the low byte of the internal data bus. And that's basically it. When we use this module in a higher level simulation, we tie this bit here to this. Same thing here, we tie, no, that's it. Same thing here. We tie this bit to this, and this bit here we tie to this, and then we have proper I/O behavior. And here I'm not showing anything regarding all the extra chips we need to drive LEDs and to select control inputs. All of that will come in the next simulator model that I will show in the next episode. For now, the last thing I wanted to mention are these inverters. These are just 6 internal inverters with Schmitt trigger inputs, just because why not? And these are the control signals that we need. So I will read them out so you get an idea of the naming convention. This is the B high load enable. Let me make it bigger so you can see better. First one here is the B high load enable. It goes in here, gets inverted, goes there, and that's the load enable input of the B high register. So when this value here is 1, then it will be inverted, will become a 0, 0 will go in here into the load enable, which is active low, so it will be active, and therefore in the next rising edge of the clock signal, this register will contain, will latch the contents of the internal bus high. And the same kind of convention applies for everything else. A high load enable, same thing for the A high. This is the external data bus input enable high. So when we want to input the contents of the external data bus into the high byte of the internal bus, this becomes 1, and then it's inverted, becomes a 0, goes down here, and enables this buffer because enabling is active low. And then the contents of the external data bus will be driven into the internal data bus, the high byte. This is the internal data bus high output enable. So when this is 1, the contents of the high byte of the internal data bus will be driven into the external data bus. And this is the B high output enable and A high output enable. When they are enabled, the contents of A high or B high respectively will be driven into the internal data bus, the internal bus high byte. And on the other side, it's the same thing, but for the low bytes. The B low load enable, A low load enable, external data bus input enable low, internal bus low output enable, B low output enable, and A low output enable. And this is it. This is a functional module for LogiSim that you can use to plug into a higher level LogiSim simulation when we build, if and when we build a complete model for Talos. Then this whole thing here will become a little box like this at a higher level in the hierarchy of simulation with certain inputs and outputs, some of which we can connect together, like the internal bus high inputs and the internal bus high output. They connect together because these buses are tri-stated. Now, one final thing to notice is look at that notice that I'm using 274 245s to drive towards the external data bus, and 2 different ones to drive the value in the external data bus towards the internal data bus. So these two, this one here and this one here, work as inputs, and these two work as outputs. But we know that the 245 is a transceiver. It can drive to the outside or to the inside, both ways. So why am I using 4? I only need 2. And then I can adjust the direction bit here. This is the direction bit. I'm grounding it, but if I weren't to ground this direction bit, I would have an output enable, and the direction bit would determine whether it goes from low to high, or A to B, or B to A, the other way around. So why am I not doing that? Well, of course I will do that in the actual circuit, but again, this is a limitation of LogiSim. It doesn't do I/O. Everything has to be either an input or an output. So to have a working model that can be used in a higher level simulation in the hierarchy of Talos, I need to split them. I even created these 245 models myself in such a way that they are unidirectional, so LogiSim accept them. But in the final circuit, we will drop this, and we will drop this, and we will use the direction line of these two, so they can work as proper transceivers, which is what the 245 is. So it can take the contents of the external data bus and put it in, or take the contents of the internal data bus and put it out, depending on how you set the direction bit. I'll go through this, I think, in the next episode. For now, that's all I wanted to share with you. In the next episode, we are going to, like we did before, we are going to grow this model here into a test bed. The test bed model you cannot use in the hierarchy of simulations. You cannot use that as a little box in the simulation of Talos, because it will have all kinds of other things that only have meaning in the final hardware, like the LEDs or the dip switches to control these control signals here in a standalone mode when you're not using that card in connection with the rest of the system. So we are going to bring in the components necessary to do all that in the test bed simulation. But if you want to do a higher level simulation of Talos as a whole, and you use models of the different cards themselves, then this is the model to use in that higher level simulation. The test bed is purely for standalone simulation, not for hierarchical simulation across different levels of abstraction. So I forgot to mention all this last time. Every time I do a simulation of a card, I'll be providing both on the GitHub repository, links in the description. We're providing both the test bed simulation and the actual model that can be used in a higher level simulation. In this case, this is that actual model. In the next episode, we'll look at the test bed and the actual design of the PCB, schematic entry, and the PCB layout itself of the register file card. So stay tuned, more next time. In the meantime, take care.